I have built a simple electrical circuit to detect the wireless energy coming out of this solid-state Tesla coil at 450 kHz frequency. This is the energy taken direct from the coil by a wire on a test light, and this is the wireless energy across the room detected by an LED and an antenna. Now watch what happens. As we turn the power to the coil off, both lights go off. As we turn the power to the coil on, both lights come on, and you can see there's several meters between this wire and the aluminum antenna. We can increase the distance between the emitter and the detector even further. Now the test light's way over here along with the coil, and the LED is about 4 or 5 meters away with an antenna. So it works over at least about 5 meters, and we're only at 10 volts. If you'd like to learn how this circuit works, which is cheap and easy and you can build at home, I'll show you now. Our solid-state Tesla coil is one of the simplest available, also called a Slayer exciter. Very easy to build in a few minutes. We just need a DC power supply, a power transistor, and primary and secondary coils of about 16 turns of 3mm wire and 1,000 turns of 0.5 mm wire. And we also need a couple of resistors, 3.3K and 1000K. What happens is when DC power goes into this primary coil like that, it also goes into the base of the resistor here. And we have a second wire from the base of the secondary coil that comes in also just in the base of the resistor near it. So when a pulse of DC goes in the primary coil, a lens pulse reverse goes to the secondary, and it makes it flip on and off 450,000 times per second. Another wire comes out and just gives you a test light so you can see if it's working. On the other side of the table, where we receive the wireless energy, we have a very simple circuit that I will explain now. Not many parts at all. I call this detection of wireless energy at 500 kHz. So here's a schematic for the circuit. Let's just look at each part in detail. First, we'll start with a 3-volt power supply, which is almost nothing, and that comes into these red and black wires into the circuit itself, and the wires are colored black and red so you know where the voltage is. Then over here we have a voltage divider, 10K and 10K potentiometer, which usually I leave on 10K all the way. And then we have another resistor here, 47K, which controls how much current will go into this transistor. And then next to it we have a little capacitor, 0.47 nanofarad, which leads to an aluminium antenna. Just a tube of aluminium. You don't need the antenna, but it brings in more power. And then that goes into the base of this Darlington BD649 transistor. Actually, it's 2 transistors. This has a gain of about 750 to 1500 in current. If you use a normal transistor here, it won't work. It has to be a Darlington. And you see the emitter goes down there. Coming up just above that, there's a blue LED, which you were looking at earlier. Then above that, there's a 100 ohm resistor just to control how much current's going through that branch of the system. So that's all it is. We have just a few resistors, a capacitor, and you can build this right at home. Now if we want to get energy out of this apart from the LED, we can tap it right here, and that will give you 45 volts AC and 450 kHz. Let's look at that on a meter now to confirm. Now I've put a single wire from the multimeter just above the LED. We follow it around, and actually this morning we're getting 0.8 volts AC. It's actually pulse DC of the multimeter. Yesterday at a lower power it was a bit less, and we're seeing 465 kHz, which is just what's coming out of that light over there. We can adjust this voltage further for special applications. And that, my friends, is how wireless energy may be detected and amplified easily at 500 kHz. Power on, power off, power on, power off. Just to be complete, I've also set up a second source of wireless energy from the same primary-secondary coil using a MOSFET that's flipping rather than a transistor. We have two power supplies, one at 4.7 volts, another at about 11 volts and 1 watt. And we're using two transistors, NPN and PNP, to drive the MOSFET and control the frequency. And you see we're getting a nice wireless light here off the bottom of the secondary coil, just like before, at 453 kilohertz. And this is the driver arrangement, 4.7 volts DC, which needs to be less than 5 because it'll turn on the MOSFET. And we have two resistors, 10K and 1K, two transistors, they feed into the MOSFET, and you put a wire from the secondary coil into one side, which is this wire over here going into the transistors. And they have a common ground, the MOSFET circuit and the transistor circuit. Now that'll also light up these two LEDs across the table, which again are detecting wireless power from here over to there. Let's see how that works. We go to the other side of the table. Now we're using two transistors in our circuit, NPN and PNP Darlington, and two LEDs to tell how each of them works. Here's a schematic. You have an antenna here through a 4.7 nanofarad capacitor, 100 microohm resistor here, and our first Darlington transistor is NPM, it's BD649. The second one's PNP, it's BD650. And the two bases are joined and the two emitters are joined. These two Darlington transistors are amplifying AC power, which is induced in this aluminum tube antenna by an emitter across the room, the wireless light, and that coil over there a few meters away. Comes through a capacitor, the AC power goes into the joint basis of these two transistors and out the two emitters, and we can tell from each light, the white or the blue, which transistor is working. They're both obviously working. Here's the circuit. We come in the two bases from the antenna with AC power. The NPN transistor sends the current forward. The PNP transistor sends the current backward. And each LED will work accordingly for one transistor or the other. The white LED registers for the PNP, and the blue LED registers for the NPN. So let's turn the current on and off and see what happens. To begin with, we can see with 11 volts going into our MOSFET circuit, we can see a direct wire gives this wireless light at 450 kilohertz, and this antenna is picking up both transistors on the other side, NPN and PNP, to make them work. Now as we change the power settings and turn the power down, you can see the bulbs go off altogether. We turn the power up again, and they come up, down, up, down, up. So it's perfectly synchronized. Now I have measured how much voltage and current are coming out of these two transistors which light up the LEDs. It's about 0.4 volts AC, but the milliamps is less than 1, quite low. So we get very low current at quite reasonable voltage. And if we want to use this system for something useful, to control some other device, we're going to have to amplify the current further. But otherwise it's pretty cool, isn't it?